Welcome back to the deep dive. Today we're jumping into something really quite amazing. It's a climate system that, well, it feeds maybe half the world's population.
That's right, and it fuels incredible biodiversity.
But at the same time, it can unleash just immense destruction. It really can reshape coastlines. It's this strange paradox, isn't it? This kind of dance between life-giving force and raw power.
A very powerful dance, yeah.
Okay, let's unpack this then. Our focus for this deep dive is tropical weather. We've gone through all the great sources you sent us, and we're trying to pull out the really key insights on this. It's a fascinating topic.
Absolutely. And, understanding tropical weather is just crucial. It doesn't matter where you live, really, because its impact, its energy, it ripples right across the globe.
So when we say tropical weather, what exactly are we zeroing in on?
We're talking about the atmospheric conditions, the sort of weather engine in the Earth's warmest zone. That's the tropics, the region between the Tropic of Cancer, that's 23.5 degrees north, and the Tropic of Capricorn, 23.5 degrees south.
Okay, so a huge belt around the middle of the planet.
A massive area. It covers parts of Central and South America, large chunks of Africa, South Asia, Southeast Asia, Northern Australia, and, countless Pacific islands. It really is the planet's thermal heartland, you could say.
And what defines it? What are the main characteristics?
Well, the big ones are warm temperatures pretty much year-round, high humidity, lots of rain, and then you get these seasonal things like monsoons or major tropical storms. It's all driven by that intense solar energy.
Okay, so if I were to, step off a plane into a tropical region right now, what's the first thing I'd notice? What really defines it day to day?
Oh, without a doubt, the consistent warmth. It hits you straight away. The tropics get the most direct sunlight all year, so you don't really get big seasonal temperature swings like in, say, Europe or North America.
Right.
Average daily temperatures, they usually sit somewhere between, let's say, 25 to 35 degrees Celsius. That's roughly 77 to 95 Fahrenheit.
And it doesn't cool down much at night either.
Not really, no. That's a key thing. Nights stay warm, often quite sticky. Minimal cooling. It creates this perpetually balmy kind of environment.
Okay, so constant warmth is number one. What's next? What gives it that thick feeling in the air sometimes?
That would be the humidity, the high humidity. It's often above 70%, sometimes much higher. And that makes the air feel, well, heavier, denser. It can make the heat feel even more intense than the thermometer says.
And why is it so humid?
It's basically down to high rates of evaporation. You've got vast, warm oceans, lots of rivers, lakes, and incredibly dense vegetation, especially in rainforests. All that water is constantly evaporating into the air, just saturating it with moisture.
Which leads us to the rain, right? The famous tropical downpours. Are they happening all the time?
Well, it depends on the specific place and the season, but yeah, heavy and frequent rainfall is definitely a hallmark. Many areas get daily rain showers, often building up in the afternoon.
Why the afternoon?
That's usually due to convection. The sun heats the ground intensely all morning. That hot, moist air near the surface rises really rapidly, cools as it goes up, and bam! You get these big, towering clouds, cumulonimbus clouds, and often a short, very intense downpour.
Wow. And we're talking a lot of rain annually.
Oh, yeah. Significant amounts. Some places easily get over 2,000 millimeters. That's about 80 inches per year. Now, some spots, like true rainforests, are wet pretty much all year. But most tropical regions have distinct wet and dry seasons, linked to the sun's position and larger wind patterns.
Okay, so that covers the sort of daily feel. But tropical weather is also known for these massive organized weather systems, right?
Yeah.
This is where it gets really interesting.
Exactly. Beyond the general warmth and rain, you have specific systems. Let's start with tropical rainstorms, or thunderstorms as most people know them. These are basically a result of that process we just talked about, rapid rising of warm, moist air. It cools, condenses, forms big clouds, and produces rain. But these can be very intense, even if short-lived. They often come with lightning, strong gusts, and can definitely cause localized flash floods.
And then there are monsoons. We hear that term a lot, often associated with places like India. What's the deal with those? Are they just bigger rainstorms?
Not exactly. Monsoons are much larger scale. They're essentially seasonal shifts in wind direction. These shifts bring huge amounts of moisture inland from the ocean, leading to prolonged periods of heavy rain.
Prolonged? Like how long?
We're talking months, potentially. Places like India, Southeast Asia, parts of West Africa, their climate is dominated by the monsoon season. It's absolutely vital for agriculture. Billions rely on it. But the sheer volume of water means it also frequently causes widespread flooding and landslides. It's a real double-edged sword.
A life giver and a potential destroyer.
Precisely. It dictates so much of life in those regions.
Okay, and then we get to the really big ones, the ones that get named.
Ah, yes. Tropical cyclones. These are the most powerful storms on Earth, really. They're huge, rotating storm systems that form over very warm ocean waters. The sea surface temperature generally needs to be above 26.5 Celsius, or about 80 Fahrenheit.
And they have different names depending on where they are.
That's right. It can be a bit confusing, but it's the same phenomenon. We call them hurricanes if they form in the Atlantic, the Caribbean, or the Eastern Pacific.
Okay.
They're called typhoons in the Western Pacific near Asia, and they're known as cyclones in the Indian Ocean and the South Pacific.
But structurally, they're the same kind of beast.
Fundamentally, yes. They have this incredibly organized structure. There's usually a calm center called the eye. Surrounding the eye is the eye wall, which is where you find the most intense winds and heaviest rain. And then spiraling outwards from that are the rain band's arms of the storm that can extend for hundreds of kilometers.
And the impact is devastating.
It can be catastrophic. They bring incredibly strong winds, torrential rainfall leading to massive flooding, and maybe the most dangerous element along coasts is the storm surge.
What's it exactly?
It's like a bulge of water pushed ashore by the storm's winds and low pressure. It can raise sea levels by many meters, flooding vast coastal areas incredibly quickly. It's often the biggest killer in these storms.
Wow. Okay, so we have these daily conditions, these specific storm systems. How does this all play out across different tropical regions? Are all tropics the same?
Not at all. There's actually quite a lot of variation. A really useful way to think about this is using something called the Köppen climate classification. It helps categorize climates based on temperature and rainfall patterns.
Okay, so how does that break down the tropics?
Well, first you have the tropical rainforest climate. The code for that is F. Think of places like the Amazon basin in South America, the Congo basin in Africa, Indonesia. These are the places that are hot and rainy pretty much all year round. Very little seasonal difference, constant high humidity, ideal for, well, rainforests.
Makes sense. What's next?
Then you have the tropical monsoon climate, which is AM. This is what you find in large parts of India, Bangladesh, Myanmar, West Africa. Here, you have those distinct wet and dry seasons we talked about. And the wet season is overwhelmingly driven by the monsoon winds bringing moisture off the ocean. Life really revolves around the arrival and departure of the monsoon.
Okay, rainforest, monsoon, what else?
The third main type is the tropical savanna climate, AW, or sometimes ES. Think of the grasslands of East Africa, the Cerrado in Brazil, or northern Australia. These regions have a much longer, more pronounced dry season compared to the monsoon climate, and then a shorter wet season. This supports different vegetation grasslands with scattered trees, basically, and different kinds of agriculture and wildlife.
So the timing and amount of rain really defines these subtypes.
Exactly. It's all about the interplay of that constant heat with the seasonal patterns of rainfall.
Right, so let's dig a bit deeper into the why. What are the fundamental mechanisms, the actual science behind why tropical weather forms and behaves this way? What's driving it all?
At the most basic level, it all comes down to solar heating. The sun's energy is most intense near the equator, hitting the surface more directly than anywhere else.
All right.
This intense sunlight heats up the land and the sea surface. Warm surfaces heat the air directly above them. That warm air expands, becomes less dense, and starts to rise, often quite vigorously.
And rising air creates low pressure.
Precisely. As the air rises, it leaves behind an area of lower pressure near the surface. And as that warm, moist air rises, it cools down. Cooler air can't hold as much moisture, so the water vapor condenses into tiny water droplets or ice crystals, forming clouds. And eventually that leads to precipitation, the rain we associate with the tropics.
So intense sun heats the surface, air rises, creates low pressure, cools, forms clouds, and rain falls. That's the basic engine.
That's the fundamental engine, yes, powered by the sun.
Are there larger sort of global wind patterns involved in orchestrating this?
Oh, absolutely. A really key player here is something called the Intertropical Convergence Zone, or ITCZ.
The ITCZ, okay, what's that?
You can think of it as a kind of atmospheric equator. It's a band of low pressure that circles the Earth near the geographical equator. It's where the trade winds blowing from the northeast in the northern hemisphere and the southeast in the southern hemisphere meet or converge.
Ah, the convergence zone.
Exactly. All that converging air has nowhere to go but up. So the ITCZ is basically a zone of intense rising air, cloud formation, and heavy rainfall. It's responsible for a huge amount of the rainy weather in the tropics.
And does it stay in one place?
No, and that's crucial. The ITCZ actually shifts north and south throughout the year, following the path of the sun's most direct rays. So when it's summer in the northern hemisphere, the ITCZ shifts north, bringing rainy conditions to areas north of the equator. When it's summer in the southern hemisphere, it shifts south. The seasonal movement of the ITCZ is what drives the wet and dry seasons in many tropical regions, like the savannas and monsoon areas.
Got it. So the sun drives the heat, and the ITCZ organizes where the major rain bands are, and that moves seasonally. What about the oceans? They must play a huge role, too.
A massive role. Tropical weather is deeply intertwined with the oceans. Sea surface temperatures, as we mentioned with cyclone formation, are critical. Warm water provides the heat and moisture that fuels storms.
Right.
And ocean currents also transport heat around the globe, influencing regional temperatures and weather patterns. But maybe the biggest ocean influence, the one that gets a lot of attention, is related to events like El Nino.
El Nino, we hear about that causing weird weather everywhere. How does it connect specifically to the tropics?
Well, El Nino is fundamentally a tropical phenomenon. It's characterized by an unusual warming of the sea surface temperatures in the central and eastern Pacific Ocean near the equator.
Okay.
This change in ocean temperature disrupts the normal atmospheric circulation patterns across the entire Pacific Basin, and actually far beyond. If we connect this to the bigger picture, this seemingly regional ocean warming can trigger major shifts in weather worldwide.
Like what kind of shifts?
Well, for example, during a strong El Nino, regions like Indonesia and Australia, which are normally wet, can experience severe droughts and dangerous wildfires.
Because the rising air and rain shifts away.
Exactly. The focus of thunderstorm activity shifts eastward over the warmer water in the central Pacific. Conversely, places like Peru or parts of the southern U.S. might experience unusually heavy rainfall and flooding. It really highlights how interconnected the ocean and atmosphere are, especially in the tropics, and how these tropical changes can have global consequences.
That is fascinating. It's not just about local weather, it's this huge interconnected system. Which brings us to the impact. Why is understanding all this tropical weather science so vital? Why should you, our listener, care about this regardless of where you live?
Well, there are several huge reasons. First, the ecological importance is just immense. Tropical rainforests, for example, cover only a small percentage of the Earth's surface, but house maybe over half of all known plant and animal species. They are critical reservoirs of global biodiversity.
And they affect climate globally too, right?
Absolutely. They act as massive carbon sinks, absorbing huge amounts of carbon dioxide from the atmosphere, which helps regulate global climate. They also play a vital role in global water cycles through transpiration, releasing moisture back into the air. So the health of tropical ecosystems matters to everyone.
Okay, ecology is one big reason. What else?
Then there's the agricultural significance. Billions of people, literally billions, depend directly on tropical weather patterns, particularly predictable rainfall, for growing essential food crops. Think about rice in Asia, bananas and cocoa in many tropical zones, sugarcane, coffee.
The monsoon connection again.
Exactly. In places like India and Bangladesh, the summer monsoon is absolutely crucial for food security. If the monsoon fails or is erratic, it can have devastating consequences for millions. So understanding and predicting these patterns is vital for feeding a huge portion of the world's population.
And beyond food and ecosystems.
There's the cultural and economic impact within these regions themselves. Weather patterns often dictate the rhythm of life, influencing everything from religious festivals and cultural calendars to farming seasons, fishing success, and even the availability of fresh water for drinking and sanitation.
But it's not all positive, as we discussed with the storms.
No, definitely not. While the weather sustains life, it also brings significant hazards. Those tropical cyclones, the hurricanes and typhoons, can cause immense destruction to homes, infrastructure, and crops. And the heavy rainfall, even outside of major cyclones, leads to frequent flooding.
So let's nail down those hazards. What are the main dangers people living in tropical regions face from the weather?
Okay, the big ones are flooding, which is probably the most common hazard. It happens during intense rainstorms, prolonged monsoons, or with the rainfall from tropical cyclones. It can inundate large areas, damage property, and displace people.
Right.
Then, specifically for coastal areas during cyclones, there's the storm surge, that dangerous rise in sea level we talked about. It can be incredibly destructive along low-lying coasts.
Okay, flooding, storm surge.
Landslides are another major risk, especially in hilly or mountainous areas. Heavy rainfall saturates the soil, making slopes unstable and can trigger devastating mud flows or landslides, burying homes and roads. Deforestation often makes this risk much worse.
And is there a risk of too little rain as well?
Yes, absolutely. Droughts are the flip side. While we often focus on the heavier rain, disruptions to normal patterns like a weak or delayed monsoon, perhaps linked to El Niño, can lead to severe water shortages. This impacts agricultural water supplies and can increase the risk of wildfires in normally wet areas. So it's a constant balancing act.
It really is incredible, the sheer dynamism and power of tropical weather. It's so essential for life in these huge regions near the equator, but yeah, also profoundly challenging and dangerous.
Indeed. It brings immense beauty, fuels that incredible biodiversity we mentioned, and fundamentally underpins global food systems. But yes, it also carries these significant, sometimes catastrophic risks. It demands constant awareness, preparedness, and resilience from the communities living within it.
Which I suppose highlights why the science is so important.
Exactly. This raises an important question, really. Understanding tropical weather isn't just, an academic thing. It's a vital, ongoing scientific effort. Better understanding helps scientists improve storm forecasting, it helps farmers plan planting and harvesting, and it empowers communities and governments to develop better strategies to protect themselves from floods, droughts, and storms.
And that brings us to a final thought for you, our listener, to chew on. As our planet changes and as our scientific understanding grows, how will we humans continue to adapt? How will our ingenuity and technology help us mitigate the risks posed by these incredibly powerful tropical weather systems, especially when you consider how vital they are for global ecosystems and feeding the world? It's a complex balance, isn't it? A challenge that really touches everyone on the planet in one way or another.